So we've gotten most of the glue off just by using the hot air gun and the chisel. And the hot air gun set to about 150 so it didn't turn to slime. We're able to sort of peel it off and then clean the remaining film off the board with a bit of isopropyl alcohol and a bristle brush. So I'm just going to go through and touch up the solder joints now, and then we're going to replace the caps, possibly do something about the silly screen grid arrangement. Let's try and get more life out of VL84s, although this doesn't have the highest plate voltage in this model, and lift these two resistors off the board, so put new ones on there with longer leads and spacers, and get a bit of airflow under them so they don't cook the board, because it's starting to discolour in that area and it'll only get worse with time. So we'll turn on the buffer. We'll get to work. So time to put the new caps in, filter caps. We've got 247 microfarad 500 volts. That's that one. Just sort of straighten the leads out and bend them, put the values pointing up. That's the other 47. Just a nice smooth bend like that. You don't want sharp corners, they could fracture in the future. And we've got 322 microfarad 500 volts. The circuit originally had 450s in there, but I've got 500 volts in stock. And it's also a added safety measure if someone ever does power it up without the valves in. The unloaded nodes may float above 450, so the 500s in there will ensure that the caps will survive that. It's a common thing on forums when you're troubleshooting your amp. People advise you to turn it on with no valves installed to troubleshoot it. It's like, well, if you don't have a variac to limit the mains input voltage, and there's no load on your preamp nodes, if you've got lower voltage rated caps in the preamp nodes, they're going to see the full plate voltage of the output valves, because there's nothing dragging them down in most amp designs, because it would be very inefficient to have a actual voltage divider supplying them. So the valve, being the load, is the bottom resistor of a voltage divider. So if that bottom resistor is not there, it just floats at the full B+, which is not good if they're rated at say 350 400 volts and they're seeing 500. So we've formed the leads, just sit them on there where they're going to go and just check if you need to give it a bit of an adjustment. It's easy to do it before applying the silicon. Avoid getting it everywhere. Just put a little smear of silicon, don't go nuts. Literally that's all you need. It squashes out when you put it down. Just check the orientation because they are polarized. Bottom it out against the board, give it a bit of a push, make sure the silicon's splooging out. On the next one, I've got my little cork blocks here. It's just like two sanding blocks from the hardware glued together, then sanded flush. Super handy for guitar work as well as amps. And we want to just push the cap down, just give the lead a little bit of a, not a 90-degree bend, just like a 45-degree bend, just to hold it in until we flip the board over. So then we'll go to C41 through 43, and they're 22 microfarad 450 volt, but in this case 500 volt. So 41 we'll start with. Wrong orientation, there we go. Again, just bend the leads over 45 degrees. Must be an air bubble in this silicon because it comes out by itself. So C42 and 43, they're next to each other up here. Having it up on the block allows you to push it all the way down without the leads hitting the bench. Oop, there goes the air bubble, I just heard it pop. It's got a life of its own. Just line the caps up so they look alright. I know it's not like you're staring at the guts of the amp all day, but just a sign of a good job. Now these ones are a bit bigger, so if these little tabs are poking out still like they are on some boards, sometimes they trim them, sometimes they don't, you want to cut them off carefully, don't affect the trace underneath. These are the 2200 microfarad. Supposed to be 50 volt, these are 63, so that's why they're a bit bigger, but it's what I had in stock. And axials are getting difficult to find, so you sort of got to take what you can get. In the future we will have to use radials and bastardize the leads over so they reach the holes, which never looks great, but you don't have much choice in the future because axials are all going obsolete, and if they're not obsolete they cost a lot of money. Like a radial will be like $2, and then the equivalent axial will be like $20. That's ridiculous. And then C65, which supplies the tremolo, which is 1000 microfarad, 35 volt. Snug down next to those jacks. So they're all installed. The other thing I did do off cam was just change the bias cap and its resistor. Had a 33k resistor. From memory these run pretty hot, so I just changed it to 39k. This will divide it to ground. We'll see where that sits, and if it's a bit too cold we'll change it back, but that's just taking a bit of a gamble on the fact that pretty much every amp runs EL84 is way too hot. So we'll take some measurements once we've fired it up for the first time. We can always have a play with that value. So we've flipped the board over. We'll just solder and trim those leads. The pads that are attached to a large ground plane. In this case the PCB has no thermal reliefs, which means you've got to just sit a little longer on the fatter traces because they absorb a fair bit of heat from the iron. So we've soldered all the new caps in place, trimmed their leads. Sorry, excuse me, I'm a bit puffed. I just pushed the car up to the mechanics. Whew. Need to work out more. So now we're just cleaning off the flux from our solder rework. It's always a good idea. Just makes it look professional. Doesn't get crusty in the bits where it gets warm. So I've jammed a bit of just paper towel into the seam there just to soak up the flux and isopropyl alcohol as it seeps down. Just give it a minute to sort of dissolve a bit, and then give it a scrub. So now we're going to upgrade the screen grid resistors. That's these two here. They're 100 ohm, 5 watt. I'll just show you the schematic. There we go. So this is a weird setup, and it's one of the weak points of these amps. So you've got the screen supply coming in here, and that's the common line for all four. That's the supply line. You've got it going directly to pin 9 of V6 and V5. So no screen grid resistor there other than the one on the screen node, which is there. So a zoom in there. What's that? 400 W5 fusible. So that's R58, which in this case is a 390 ohm. So that drops it down quite a bit to the screens, but you've got hundreds on V7 and V4. don't try and figure out the numbering on these things. 4, 5, 6, 7, yeah. So you've got screen grid stopper resistors, I guess you could call them, on V7 and V4, and then none on V5 or V6. So that runs these a little bit harder, but 100 ohms is a little bit optimistic too. Screen grid failures on EL84s are, in my experience, the most common failure, shorted screens. So I'm going to upgrade them, and I'm going to insert some grid stoppers on V5 and V6. Okay, so we've removed the two existing 100 ohm 5 watt screen grid resistors. They supply the outer two valves, so V4 and V7. This one is, which way does it go? V7. We go pin 9, which is the screen grid pin. And we've got continuity there. Now, if you're using a continuity tester, just be aware, if you still have these resistors installed and they're 100 ohm, depending on which model of meter you've got, it might still beep, or it might be a shorter beep but not a extended, ongoing beep. So if I test with this meter, that doesn't beep at all at 103 ohms, but some of the cheapo ones do below a certain threshold, like, I don't know, 100, 200 ohms or whatever. So just be aware of that. I've removed the resistors completely, so that's irrelevant, but just be aware of it. So that used to go to that end of R53, and we'll go V4 as well. That goes to, you can just wipe your contacts long until you hear a beep, check that it's 0 ohms. That's your other connection. That wriggles down below some components here. That's that one there. It makes it through a jumper to that end of R43. Now both this end of R53 and R43 are connected, and that is the supply line to V5 and 6, which don't have a screen grid resistor. So what we need to do is insert one between that point and those two. So how do we do that? Well, let's figure it out. So here's the two on the top of the board. They were easy. We can just pull out the 100 ohm existing ones and put in our 1K 3 watters. Chosen 3 watters because they're a bit more lightweight and a little bit more compact. And you can see there I've lifted them off the board a bit to allow airflow underneath them for cooling. So those two are easy. The other two not so much. So what we had to do for them is break a trace. So the two pin 9s on the inner two valves, they are connected via this trace. You can see I've cut that there. Put a little bit of conformal coating over that just to seal it up if there was any fiberglass exposed on the edges of the trace, just because that does have a high voltage on there. We don't want it tracking to anything else. And then I've mounted the screen grid resistor for this one directly to the valve socket, so I've passed that through and given it some mechanical support by folding the lead over there, and siliconed it to the board as well, just so it's not flopping around. There's a good 5mm or so between that exposed trace and that. There's no way it can touch, especially with the silicon now cured. Then I've run a wire to the common supply point here, which finds its way to this trace here and that link, and then that's the supply line to the other two resistors on the other side of the board. So that's the screen supply line, and then it splits to these two resistors which go directly to pin 9 of the inner two valves. So that's how we get 1K screen stoppers per valve. And really I think that's the most elegant way of doing it with this board. The best way of doing it is on my new board, where there's a single resistor for each valve right next to it. But you know, that's my upgrade. Can't expect Peavey to do that for, you know, less than $1,000 amp. Right, so now's the tricky part. We've got to run this unit on the bench, opened out, just to check everything's cool before we put it back in the chassis, however you want to say it. So the best way to do that is to undo the power training. I've just done that and found a bunch of stripped holes, so that's nice. We're gonna have to put some proper hardware in there instead of the self-tapping tri-lobe pieces of shit they give you, because the actual thread in the transformer bottom plate, which is spot welded to the laminations, they've stripped out. So it's a good idea to have a proper bolt on there anyway. So we're doing this to get a bit of extra length on these connections, because what they do is they run the wires from the transformer into the chassis through the grommet, and they crimp them afterwards, so it means you can't fit the cables back through the hole from whence they came. So yeah, that's fun. Now this one here has to go on that one. That's the secondary. Primary is easy to fuck up. So you get it the wrong way and the feedback will make the amp oscillate. So take note of which way they're on before you remove them. Actually, come to think of it, I've got to check myself. We're just about to put the valves back in. Just noticed a bit of corrosion on the pins, particularly on that ruby to the left, but also on that JJ's to the right. You can see the pins aren't very shiny. So I just give them a hit with bronze or brass bristle brush. So it won't hurt the plating on them, but it'll just take off any shmoo that shouldn't be there and shine them up a bit. Just gives them a bit of a polish, bit of a buff. Those pins are all tilted over to one side. You can see they're all a bit pushed over, like it's been shoved sideways while it was in the socket, so we'll straighten them out. Be careful not to crack the glass in the base when you do that. And also be careful not to get any brass bristles into your circuit board, because they do conduct. Right, so we've got a new set of EL84s, a match quad in there, JJ's, and we're reusing the preamp valves just to save a bit of cost. We'll reuse them if we can, if they're not noisy or whatever. So this amp, well, any small circuit board amp like this, generally all the cathode connections will be connected for the output valves. They'll have a common ground. This is a fixed bias Class AB amp, so the cathodes are connected directly to the ground on this board. I believe it's the leftmost connector, that one there, and it's a bit difficult to check the current or check the bias of the valves. Normally you'd use Novel probes. So here are some octal ones. They're Euro tubes. They actually break the connection between the anode and the socket, and you can monitor directly through the milliamp or the current setting on your multimeter exactly how much current they're drawing. They're probably the most accurate way of measuring. However, we can do another method here called the transformer resistance method. Now, every transformer's got its primary impedance. That's what everyone quotes for each amp design, 3K, 8K, whatever the impedance is, but they've also got a DC resistance. In this case, 123 ohms on that side. You can't see the meter there, can you? 123 ohms that side, and 94 ohms on that side. So that's the DC resistance. A lot of people trip up, they think, oh, it's out of balance, something's wrong. That's just the amount of copper between, or the length of copper between each side and the center tap. That's not the inductance or the impedance of each side. That is determined by the turns ratio and the geometry of the coil. So you can have the DC resistance being out significantly from side to side, as long as it's not ridiculous, like several K or something, or like open circuit, then you've clearly got a problem with the output transformer. But they do vary quite a bit. So what we've got to do is we measure each side's resistance, we note that down, we measure the voltage drop across each side, and then we divide the voltage drop by the resistance, and that gives us the current. And then we measure the plate voltage from ground to plate in this case, because being fixed bias, that's the cathode, is ground. And we multiply that by the current that we measured. That gives us the watts per side, the dissipation of each pair of valves. And then we can divide that by 2 to get the dissipation for a single valve. And then we can get that and divide that by the maximum dissipation on the data sheet. So that will give us the percentage of maximum safe dissipation. So that's what's often quoted by techs when they say, where's the bias? We'll talk in watts, and we'll say, well, we won't talk in watts. We'll either talk in watts or we'll talk in percentages. We don't talk in milliamps, and we certainly don't talk in millivolts, talking about measuring across some unknown resistance. So you want to talk in percent, otherwise, well, percent or watts, and let the person you're talking to figure it out. But we don't want to talk in milliamps, because that's not taking into account the plate voltage, and it's not telling you how much power that tube is dissipating. So let's get to it. Right, so here I've got the meters set up, so we've got some convenient connections on the links between the two boards, and we've got the negative of each connected to the B+ node. So just to confirm that we've got the right connections, we've just set it to resistance, and it's giving us the same readings we were seeing before. So now we can switch that over to volts, and we'll set up a third meter as the plate voltage, and then we'll be able to calculate our dissipation from that. Alrighty, so we've got the variac set up. We're plugged in. We've got these 2 meters checking the voltage drop across each side of the output transformer. We've got this probe free. Got the ground connected to the ground and the SIR on the B+ node caps. So we can go through and just check that all our voltages are present. Fire it up. Check the dissipation on the watt meter. Bring it up a little bit. It's only going up to 7 or 8 watts, so I don't think we've got any dead shorts there. On our plates, we've got 56 volts at the moment and rising. We'll just check our control grids on the output pairs, if I can find them. It's got minus 1.5 there on JP 532, so that's one side. I think it's that one, minus 1.5 on JP 619. Just monitor that as we bring it up a little. Be careful not to touch anything, don't let your hands wander. Yeah, so it's going more negative, so we've got bias supply, no problem. Minus 2.9, so we'll keep going. 128, we're drawing 15 watts, slip with the probe there, you got to watch that. 16 volts. Watts, sorry, we've got 180 volts on the B+, 20 watts, that's the heaters, starting to draw more current as we bring up the voltage. Meters are starting to move, monitoring the voltage drop on the output tranny. Should start to hear some signal soon. There it is, 1K. 250 volts on the B plus. Now watch this. Breaking in oscillation. Drop that voltage back and can't sustain it, not enough gain. So that tells us the output transformer is plugged in the wrong way, because you do have the ability to put that plug in both ways, and if you put it in one way and guess, you're pretty much guaranteed it's going to be the wrong way. It's called Murphy's Law. So we'll let that drain off a bit, we'll disconnect it, come back, check the voltages. When it's safe to work on, we'll pull that plug out, turn it over, and then I'm pretty confident we can just give it full mains after that, and we can start taking some measurements and figure out where the bias point's sitting. Alright, so we've switched our output transformer primaries, the connector 180 degrees to get rid of that oscillation. So now we'll fire it up without the variac and we'll take some measurements. She's drawing 70, 50, down to 50 watts. Now starting to rise again as it conducts. We'll check the B plus, 385 dropping as they conduct, and we've got our voltage drop rising here as everything warms up. We'll check our actual plate voltage once everything settles down. So about 374, 373, and we've got about 4 volts and 4.9, or 4 volts and 5 volts across the either side of the transformer. Okay, that plate supply's settled down now. So let's calculate that. So on the left hand meter we've got 4 volts and we had 94 ohms on that one, so we go 4 divided by 94, and that gives us 0.0425. So that is in amps, because it's Ohm's law, so that equates to 42.5 milliamps. So we multiply that by the plate voltage, which will round up because it's 375, bit of a safety margin, the mains does fluctuate. So that gives us 15.95 or 96. So that's the wattage for both of the valves on one side, well, both the outer I think in this one. So we'll divide that by 2. We've got 7.9 watts per valve. So the maximum for an EL84 is 12 watts. So we'll divide that by 12. So that means we're running 0.6648. So that means 66.5% dissipation per valve. So that's good. We'll go to the other side. We'll go 5 volts. Yeah, we're around. Well, we'll get 5 volts. Round it up. Oh, let's go fancy. Let's go 4.9. So 4.9 volts divided by, it was 123 ohms, equals 0.398. So that's 39.8 milliamps. Multiply that by the plate voltage, gives us 14.9 watts. And that's that's for 2 valves. So divide that by 2. 7.46 watt. Fraction of 12 watts is that. That's 62.2%. So pretty reasonably close match. So we're running around 62 to 65%. So that resistor change in the bias supply was pretty well bang on. Perfect. So well, we've got it fired up. We know it's not going to fry itself. Just check for microphonics. So something's microphonic there. Can be hard to tell what valve it is when things are so sensitive. It seems to be most sensitive on the ruby. You can lightly touch the JJs and it doesn't do it, but you lightly touch the ruby and it does it. So I think we'll at least change the ruby out. I did change the fuse as well, because when one of those valves lost its vacuum, that took out the HT fuse. I went to change the 3 ohm resistors, but I have one. I need 2 in stock. So I'll have to order some of them and wait for them to come in. Joy at the moment with postage the way it is. And then I think we can start looking at cleaning the chassis and reassembling this thing and getting it ready to send out. I'll give it a sound test as well. Things are a little bit noisy at the moment because grounding's not great because it's not in its chassis. What I might do is I'll change that valve out, check that that's addressed the microphonics, and then we'll just play a little bit of guitar through it and see what it sounds like. So it just popped in the JJs and match the other 2. Microphonics gone away. So it was that Ruby valve. Bloody Ruby, it's the odd one out. It's getting jealous of the JJs. So now she's nice and quiet. Let's just crank it up a bit. I'll turn off the signal, Jenny. We've got an inevitable amount of buzz there, just from the thing being open on the bench. So we're not going to learn a lot about the noise floor of this thing until it's back in its chassis, but that doesn't sound like there's any ridiculous noises happening there. Of course it's humming when I touch it because the pot shaft isn't grounded. So I think we can safely get that one back in the chassis once we get those 2 resistors replaced. And we can call it a day on that one. Just drill out these holes to suit a 4mm machine screw. Just taking a fraction off there. The holes that were stripped were pretty much already 4mm. Got an M4 machine screw with a washer on the bottom side, flat washer, and a nylock nut, just to make sure she don't come loose again. Just use the ratchet there, makes it a bit quicker. Little Sid Chrome 1/4 inch mini ratchet. It's a little weapon. Those tight spaces. Just give the front panel a gentle clean with just a moist rag. Be careful not to take that writing off, it's already pretty pitted. So anywhere where there's pitting, if you're not gentle, you'll take the writing off as well. I mean, it's a matter of time till it all comes off. I mean, look at the rust. That's literally rust coming through the pitting. So we'll wipe off the excess. You can still read it for the moment. Give it a little bit of a buff. And the only other option is if it gets much worse, I think you can get like for the Fender Blues series, you can get like printed overlays or like vinyl stick-ons, or if not, might be a possibility of getting some printed up in the future, just vinyl wrap that you put over it. This is pretty good nick though, comparatively to a lot of them I've seen. A lot of musos don't care, they remember which knob does what and set and forget it anyway. That's alright, looks a bit better. Alright, so we've folded it back into its origami shape, like a swan. And we'll just go through and just double check that none of the wires are broken or none of the solder joints inside have been stressed. And they're looking all good, so we're right to reinstall it. Alright champions, so we've got the thing back in the box, oh it's chassis, sorry. We're gonna fire it up and have a quick listen, just check the reverb, check the sort of noise floor, sort of, even though I'm standing right in front of it. Got everything in midday, noon, except for the normal and the post control. Even the tremolo, set at about 12 o'clock. Tons of reverb. Tremolo. Pot taper of the tremolo seems a bit silly. It doesn't change much until you get to about 8 or 9 and then it goes through the roof. I'll turn that down for a sec. Massive decay on the reverb. A little bit more hum, of course, when you turn the reverb up. It's probably the longest decay I've ever heard. Doesn't sound like any overdrive on the reverb sound, so that's good. Turn the reverb off for a minute just to get a sense of the noise floor. Let's crank the normal up. So moving away from the amp, it's almost completely dead quiet there, a tiny bit of hiss, but no hum or buzz, so that's great. So that's just the normal channel. Let's switch over to the overdrive. So these have got a really nice sort of EQ curve, post distortion, which is why everyone likes them. There's no ice pick and it's also not dull like a tube screamer. It doesn't have the filtering where they've obviously removed a lot of the top end for oscillation or just harshness reasons. It's got a nice rounded old school tone. Crank up the pre all the way, just check there's no oscillation or anything. So that's a pre all the way up and post at 12 o'clock. That's these pickups, not the amp's fault. Let's check the tremolo on that channel. That's the boost control. So there we have it. Next I'll just fire it up into the dummy load and check the maximum power output. We're still drawing the 85 watts from the mains at idle, so having the watt meter there is good just to give you an indication if anything's gone out. Once you've reassembled the thing, you don't have the bias probes attached. Yeah, so I think we're going to just test it for the output power and then we'll clean up the box and stick it back in the cabinet. And out she goes, on to the next one. Another interesting thing of note here is 16 ohm minimum load, 30 watts RMS. Even the output transformer was designed to cut costs. So if you've got a 16 ohm load, that means you don't have to have as thick gauge wire because you're not dealing with as much current. It's getting the same amount of power but using the voltage to make up that half the equation. So you can have finer gauge wire and you can have a smaller output transformer. So everything they did was cost cutting but with minimal compromise. So all they had to do was just put a 16 ohm driver in it as opposed to an 8, and they've saved some money. So pretty smart. Alrighty then, we've got the good old function generator, 1K sine wave. Going into the clean channel, we'll fire it up. Test for output power. Let it warm up. Let's scope up here with the AC RMS volts displaying on the little vacuum fluorescent display there. Isn't it pretty? And we're bringing her up. So it's still warming up a little. We're up to 84 watts. Hovers around 84, 85. So everything's hunky-dory still. Excuse me. Right, so we'll bring her up. We'll check where it starts clipping. Flattening out a bit there. We're at 24 volts. 24 volts RMS. So we had 24 volts RMS going into 16 ohm resistive load. So we go 24 squared divided by 16, 36 watts. So pretty healthy considering it's only supposed to be putting out 30. Happy days. So back in the cabinet she goes. After vacuuming the cab out, I like to just get a slightly damp sponge and just take off the excess dust that the vacuum can't seem to get no matter how much you brush it. Don't go getting water everywhere. Just wipe out the bottom. Just seems to be that dust that just won't be moved by a brush. Get in the corners. And then give her a quick dry. Bit of terry toweling. You can see the paint starting to blister and corrode underneath. That's pretty much inevitable on these units. They're Eminence OEM units. They all seem to do the same thing. Speaker upgrade's an option, but you know, in this case, if it works, we'll keep the budget below that. Give the reverb tank bag a bit of a clean as well. They always get gross. Alright, legends, thanks for watching. Share it around, subscribe, blah, 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 all the same shit, you know. And I'll see you on the next one. You know where to find me, eh?